All right, here we go. This is lesson 1. It's from section 4.2, the first lesson that we're really dealing with since we've gone online. And what I want to do is I'm going to read through some slides and talk about some concepts. So you might want to get a piece of paper out and pencil. These slides are up on Sapling though, so you can go back and look at them again. It's section 4.2 slides. I'm going to go ahead and read through some of the presentation, the slide presentation, and then work through an example to show you the kind of information that's needing to be done to solve the problems related to what we're getting into here. So here we go. All right, what I want to do, first of all, is turn on the slideshow. So we're going right here. So let's go right here. So we're starting into chapter 4 from the text, all right? And the first thing we're going to be talking about, this is section 4.2, maximum and minimum values, critical numbers, and those are the two key concepts. And so the first thing we're going to do is identify what absolute maximum and minimum values are, and what local, they use the word extreme, but they're just saying the same thing, local maximum and minimum values. They use the word extreme, and they'll use the word extrema in a second. But the idea is that it's talking again about maximum and minimum values in a particular region. When we say local, we're saying in a close region, just a small segment of the graph. We're going to find critical numbers, and we're going to actually find absolute maximum and absolute minimum values of a function. So let's take on a particular interval. Let's look at, for an example here, let's look at the definitions they're giving. So you might want to make note of this. And so the situation is absolute maximum and absolute minimum of values are given there. Let f be a function divide on any interval. If there is a number u in the interval for which f of u is greater than or equal to f of x for all x and I, in other words, the value of the function is bigger there than any place else in that interval, then it's called, f of u is called the absolute maximum value of f on that interval. And going the other direction, if there's a number v, they chose a different letter there, v instead of u, v in the interval for which f of v is less than or equal to f of x for all x in the interval, then f has an absolutely minimum value at v. At v, and the number f of v is the absolute minimum value of the function. So notice there's two different terms there. You're finding the absolute value of x that it is occurring at, and you're also looking at what the absolute value, what the absolute function value is at that value of x, whether it's a max or a min. So the values f of u and f of v are sometimes called absolute extrema, maximum min, or the extreme values of f on I. Let's go ahead with this section. And you can see, take a look at this graph. You can see what they're talking about there. On this interval, the blue is showing that it stops on the end. A and B are the endpoints. And on that interval from A to B, the absolute max is happening up at that peak at u f of u. And the absolute minimum is happening at vf of v, the lowest place on the function. That's what absolute max and minimums are. And that's the key idea, all right? Now, when you talk about local maximum or minimum, then you're talking about, let's back up just a little bit. If this function off to the left there, to the left of A, if it continued to go down all the way down past where the current absolute minimum is, then the absolute minimum will no longer be the absolute bottom, the absolute minimum. It turns out it would be then what is called a local minimum. In the immediate area around that point, it would be called a local minimum. And as a result, local or relative minimum is what's the term that's used instead of absolute. So there's possibly something that is more minimum. It's smaller somewhere. But in this immediate area, that is the local minimum value. So that's the main idea there. And I'll come back to that if you've got questions. So the local is that if you have an interval, the wording here gets kind of clumsy, but everything close to that value, it is the lowest. It is the smallest value you can get, anything close to it. And for the maximum, same situation. You have anything nearby, really close to it, it is the highest value in that little region. That would be called a local or relative max, okay? And local extreme values. So here's another example where if you look at U1, it's at a peak there, but it's not the absolute max of that function, because there's another place over at U2 that's higher. So it's not an absolute max, but that would be the local max in the area right around it. That would be called a relative maximum value. And at U2, that would be the absolute maximum value. And again, now look at this, V, notice how it dips down, but there are places to the far right and far left at A and B, for instance, that are lower. So it's not the absolute minimum, but at V, it is called a local minimum value of that function, because all of the points immediately around it, that V gives you the lowest point in that local area. Okay, that's the absolute and local max and min kind of idea. We can talk about that more if you'd like. I'd like to go on to this situation right here. If you have a particular interval, so for instance, in this situation, we've got the domain. Notice the open circle down here at the far left value of the function. And you got a closed circle every place else, everything's filled in. So the domain is showing an open bracket on -6 and closed bracket on 9. Notice it's continuous on there. That's part of the constraint that has to be happening here. The absolute maximum value of that function does not happen where the curve is going through the y-axis. There's a relative max there, but if you go over to x equals 9, you go up higher. Therefore, the absolute max occurs at x equals 9, and the absolute maximum value is 10. The absolute value of 10 occurs at x equals 9. And the absolute min, you notice here, there's two places that appear to be getting down to 1.3. Notice at -6, but it's an open circle. So therefore, that point isn't included. And 6, 1.3 is a little bit lower than anything over there to the left. So it's called a local minimum value also because anything in the immediate area is that way, but it's also the absolute minimum value because it is the absolutely lowest point of that graph. Notice the value of x, it occurs at x equals 6, but the absolute minimum value is 1.3. All right, that's the key idea there. It looks like there's a typo there on the screen. It says local maximum value 6, 1.3. That should be local. Absolute min and local min are the two situations there. And a local maximum, wow, they got another typo. The local max value, a local max is at 0.8, the value of x. And at x equals 0, the y value of 8 is a max. And in the immediate area around it, there's something higher over at 9, x equals 9. But around the area x equals 0, the highest point, the local max is at 0, and that value is 8. So they've got a couple typos on that screen. I'm sorry about that. And I'll extreme that. But here's an extreme point to remember is that an extreme value theorem. If a function f is continuous on a closed interval, then it has an absolute max and an absolute min. It's got to happen. If it's continuous on a closed interval, it has to have a max and a min, absolute, highest point and a lowest point. That's all it's saying. It's got to have that. So that is the fact of the situation. And the conditions for the local max or local min now is that if a function has a local max or local min, then the derivative at that point, the slope is equal to 0, or the derivative at that value of x doesn't exist. All right, so that we can, and you can see the examples they give here. At x1 and x2, the slope is 0, so therefore those are local maximums or minimums. And x3 is also got a situation there that can be a local max or min. It turns out that is a local max, and the f of c does not exist. The derivative does not exist because you can see the slopes they're not the same if you come in from the right and you come in from the left. You can see that x and the red writing there. So let's look at an example. All right, I've put that problem right here. I've put on the board, so I'm going to resort back here and get back to talking to you live. Hello, hello. And if something wasn't clear about that, you can go back over it and clarify things. But this is the problem that was just on that, given on the sheet. And the idea is it's saying determine, this is local lesson 1, section 4.2. So the situation is, what we want to do when we're trying to locate, let me go back to what the assignment said there. What did it say to do? It said, find any critical numbers for this function. All right, so we're going to find the critical numbers for that function. And the idea is, what you got to do, since this is a polynomial, and therefore it's polynomial, it's continuous everywhere, then for this situation, all we got to do is take the derivative and find out where that derivative is equal to 0. So that's the goal of the situation. I've been talking about it throughout the semester. Take the derivative, set it equal to 0. That means you got to factor it in order to find out what caused it to be 0. So let's take a look at this. Let's take the derivative of this. All right, and I know you're kind of familiar with this by now. A little refresher, get the rust out of hinges a bit. We got what, 3x squared, 2 down makes this minus 12x to the first plus 9. All right, so there's the derivative. And it's not obvious by just looking at that. We've got to factor it to find out what causes that thing to be equal to 0. And notice that we can factor out a 3. 3 is common. Let's factor that out. And now we can factor that into two binomials that in the reverse FOIL kind of a moment. What is that? So it's got to be x and x in the front. It's got to be 3 and 1 if it's an integer function. And it's minus in between, so it's got to be negative. So as a result, we have just factored it. And now we need to determine what causes this derivative to be equal to 0. Where is the slope equal to 0? So what we do is just set this equal to 0. And this 3 isn't critical in doing that. But I'm going to include it as part of the problem. We can ignore it really, because the only way this could be equal to 0 is if x minus 3 equals 0, or x minus 1 equals 0. And that's going to happen at x equals 3 and x equals 1. So the question was, what are the critical points? And one way to answer that question is the critical points are x equals 3 and x equals 1. Those are the places where the slope is equal to 0. So let's see what's going on with that. I'm going to also put that up on a screen and take a look. Let's take a look at the graph of this function. We said the critical points are at x equals 1 and x equals 3. First of all, you tell me, stop and think about this. What does this graph look like? What does we got a cubic, right? And it's not just x cubed. X cubed looks like this, It looks something like that in general. But this has got other things, other circumstances that are in there, other things that have been added and subtracted from it. And as a result, we get a little contour in the situation. So it turns out we get something that might look like that, okay? Notice that it's going off to the bottom left and it's going off to the top right. I hope you thought about that, yourself when you saw that it was an x cubed function. That's the thing to recognize. So it's going to look something like this. So let's take a look on I got a Desmos file up here. Let's take a look at what this function actually looks like. I hope you can see that. Okay, take a look at how the screen is set up there. You can see that the curve is set up in such a way that you can see that the top, the local maximum that's there in that curve is over at, you can see it's at x equals 1, and it's up at y equals 9. Let's zoom in just a little bit and see if we can get some numbers, a little more detail on that. Okay, yeah, 9 shows up and 1 shows up. 1, 9 is a local max, and 3, 5 is a local min at x equals 3 and at x equals 1. All right, so those are the critical values that we saw in the situation. Now, they are local because you can see, like I was saying, that let's go back to so what I was pointing out to you is that there are values. See, this is a local max. This is a local min. But there are higher points than this local max, and there are lower points than the local min. So it is just local, not absolute. And in a second, I'm going to do a second problem that has to do with on the interval 0, 2. Notice what would happen here. This is at 1. This is at x equals 3. So on the interval 0, 2, we've got something like this. So on 0, 2, it ends up that you've got another circumstance that you've got to contend with. So we'll deal with that in just a minute, okay? All right, that's lesson 1. I'll talk more in just a little bit about going a little further with this problem, all right? All right, thanks.